Hello there, my name is Damián Dellavale. I am a postdoc at the Institute of System Neuroscience in Marseille, France. In this presentation, I will introduce a new tool for detecting and clustering epileptiform events. Importantly, this tool might be relevant for analyzing different types of recordings in clinical applications. The problem of detection and classification of epileptiform events is relevant for both clinical applications and basic neuroscience. Our strategy to address this problem is schematized in the figure on the left. The algorithm processes the recordings to detect the prevalent waveform shapes present in the data. Then, a series of nested clustering stages are applied sequentially to group the events based on time scales, waveform shapes, and finally, a fine-tuned classification can be performed based on specific clinical criteria. The figure on the right shows the layout of the proposed algorithm. The input data goes through a detection loop which filters the data using two types of kernels. The first are extrinsic kernels used for time scales decomposition. These kernels are defined a priori by the user. The second set of kernels are intrinsic to the dataset, and these intrinsic kernels change over the iteration of the loop in order to explore different waveform shapes present in the data across the time scales externally defined by the user. In the upper part shown here, we analyze the consistency of the detected events over the iteration of the loop, and then several clustering stages are applied sequentially to obtain the final classification of the events. The algorithm was first tested using realistic synthetic signals described in the paper of Roeri published in PLOS ONE in 2017. This dataset captures two relevant aspects regarding the emulation of experimental recordings. The first one is the level of the background noise, and the second one is the variety of the waveform shapes. The performance of our algorithms in terms of precision and recall is shown in these two figures at the bottom left. In the upper right part, you can see a confusion matrix. This confusion matrix was computed for signal-to-noise ratio commonly found in experimental recordings, and it shows that our algorithms does a very good job at classifying the waveform shapes present in the data. In these plots at the bottom, you can see the raw signals of some clusters corresponding to this confusion matrix, and also you can see the average power spectrograms associated to each cluster. The algorithm was also used to process experimental recordings in a mice model of epilepsy. The clusterization based on time scales managed to group the artifacts in specific clusters. On the other hand, the events with high content of spectral energy in the ripple and fast ripple frequency bands were grouped in different clusters. The clusterization based on time scales does a very good job at segregating most of the artifacts, but does not solve the problem completely. Since all these events share very similar fingerprint in the power spectrogram, the key point to note here is that after you have these clusters based on time scales, an efficient approach to segregate the waveform shapes present within these clusters is to compute another clusterization process on the raw time series of the events rather than using the time frequency representation. Let us focus on this particular cluster here with the red asterisk. The nested clustering based on waveform shape was implemented as follows. We first computed a principal component analysis on the raw signals pertaining to this cluster, and then the original signals were projected onto a subset of principal components. Finally, clustering via k-means was computed in this projected space. The matrix of period distances computed on the projected signals reveals that different waveform shapes are present inside this cluster. This nested clustering procedure effectively segregates the oscillatory events in a single subcluster. Then, a fine-tuned classification can be performed based on specific clinical criteria. For instance, we can count the number of oscillatory cycles present in each event in order to compute a further classification. We also use the algorithm to identify interictal spikes in stereo EEG recordings from epileptic patients. We found that our algorithm managed to group the putative interictal spikes in one cluster, and the sharp events classified as no spikes by the epileptologist were segregated in a different cluster. These preliminary results suggest that the proposed tool has several advantages that might be relevant for clinical applications. Specifically, the algorithm has a few critical hyperparameters. It is based on a weak supervision paradigm, and it showed particularly good performance in clustering the prevalent waveform shapes present in experimental recordings corrupted by a high number of artifacts. Thank you for your attention, and do not hesitate to contact us. Your comments are more than welcome.